Thank you very much. Welcome. Good morning, everybody. I'm trying a new thing here for slides. I mean, I'm not doing like Open Office or whatever the Mac thing is. What is it called? Keynote. I'm not doing that. These are HTML pages. And so if you want a copy of these slides, you can visit that URL down at the bottom. And then you'll get a little menu. Well, I can just click on it and show you. You'll get a little menu here. And you can view the slides by clicking on that link, or you can download a tarball or a zip. Or if you want to, and you're comfortable with Fossil, you can, that's a Fossil repository. You can just you can clone the whole thing, and then you can have it. So don't know how this is going to work, but we'll give it a try and see how it goes. Oh, and the CSS that we're using works really well, so that if you just want to follow along on your phone or something, I mean, it scales appropriately and everything. So we'll see how this goes. The talk today is on optimizing the Tickle core. Make things run faster. I know yesterday Donald was talking about how we've got this challenge to make Tickle run faster. And he and Kevin are working on really cool algorithm changes. And this is not, what you're doing is not a microoptimization. You're like going, you know.
We're shooting for the moon.
You're shooting for the moon. This is a totally different approach, and it's a complementary approach. And I came across this in my work with SQLite. Now, I don't know if you're aware. You know, I haven't done a whole lot of Tickle lately because all my time is taken up with SQLite. You've probably heard of SQLite. You might not be aware that SQLite is a Tickle extension that escaped into the wild. It began life as a Tickle extension, and then later on I put it out there as a standalone library. So that's the connection. So this is a graph of the CPU cycles used by SQLite to do a standard workload over time. And these are different versions of SQLite. So going back 8 years, you can see that it was using almost 2.5 billion cycles for this particular workload. And you know, there were some companies that were encouraging us to make it go faster in here, and it got down here, and about along in here, we figured out that's as fast as we can make it go. We don't know any way to make this thing go any quicker. But about 3 years ago, I came across some new techniques for optimizing code. And as you can see, since then, we've essentially doubled the performance of SQLite in terms of CPU cycles. It looks like it's almost a straight line here going down. So we can project this out, and you can see clearly that by the year 2020, SQLite will use no CPU cycles at all. And you laugh, but in my country, there's a lot of important people who make decisions based on that kind of reasoning. So,
not only in your country.
But so the question came up, you know, is it possible to do similar sorts of things with Tickle? Because, you know, that would be really cool, because you don't have to then change your scripts or anything. You just, you know, update to the newer version of Tickle and run it, and suddenly your programs run faster. And this would be a really big benefit, because there's lots and lots. So if you're optimizing the Tickle core, you're going to be improving lots of different programs, not just a single program. So I wanted to spend some time in talking about what are some of the techniques that we use to get SQLite to run twice as fast. Let me just emphasize that that previous slide was talking about CPU cycles. It wasn't measuring real time. It was counting actual CPU cycles. And so if there were delays for I/O, and SQLite really is kind of dominated by I/O, you know, using fewer CPU cycles pulls less energy out of the battery, but it doesn't necessarily reduce the amount of I/O. So there's a difference there. But with Tickle, it's not really I/O bound; it's more compute bound. So any CPU cycle reduction you can get in Tickle is actually going to probably give you a good performance boost. So the first thing to consider about this was the idea of an amalgamated source file. I don't know if you're familiar with SQLite, but there's about 100 source files to the library. But for delivery, we take all of these source files and we concatenate them all together into one great big C file, which we call the amalgamation. And there's a couple of benefits to that. One of them is that that makes it SQLite much easier to use, because if you're developing a project, you can just take this one source file, drop it in, and compile it with the rest of your project, and you've got a database engine built in. You don't have to have a separate make file. You don't have to deal with libraries and all these other dependencies. But the other big advantage is that when you put all of the code in one big source file, it becomes a single translation unit. And then the compiler is able to do much better inter-procedure optimizations. And this chart shows that. This is a different workload, so it's got a different number of CPU cycles. But here, I've run this is the same workload in all cases, and that should say billions of CPU cycles, by the way, or millions of CPU cycles. I've run it with compiled for, optimized for size, and then when I do -06, I mean really, GCC and Clang, they really don't take anything bigger than -03, but it's always traditional to do -06 because you never know when GCC might add -04. And it always rounds it down, and it just works. So -06 means every possible optimization is turned on. And with separate source files, the difference between -OS and 06 is only about, it's less than 1%. It is a little bit faster, but it's not that big a deal. Now, and then I ran the same test, but on this time, I compiled SQLite into a single big source file and compiled that. And as you can see, from the baseline, it improved 5%. But furthermore, when we turned on all of the optimizations, the optimizations were able to do a much better job, so that we can actually get almost 7% improvement just by concatenating all of the files together and running it that way. So that's something that I think would be a relatively easy project for somebody to undertake, an amalgamated version of Tickle Shell. Now, the way this works.
Just one question. Don't
Sure.
you run into some limitations regarding the maximum file size?
All right, so the question was, do we run into limitations? On GCC and Clang, no. On MSVC, it compiles fine, but your debugging information is limited to a 16-bit integer for the line number. And so it starts wrapping. So there is an alternative approach to that, and I'll talk about that in a minute. Don't let me forget. But let me get through these slides, and I'll talk about how we can work, how you can work around the MSVC limitation. So the way this works is, for SQLite, we've got 100 or so source files over here, and then I've got a Tickle script, and the Tickle script just reads in each of these source files and concatenates them together, and it has to make some subtle changes because it doesn't want to have the same header file occur multiple times. So it remembers header files that it sees, and if it sees it again, it comments it out. Or if actually the first time it sees it, it actually goes and grabs the header file and inserts it in line if it's one of the project header files. And so so this in SQLite turns out to be about 200,000 lines of code total. And that includes comments. If you take out the comments, about 140,000. So it's a big file, and it takes a couple of minutes to compile on a fast machine, but it's really convenient. You could do the same thing with Tickle. And in fact, here's the script that does it. You can click on that, and it'll take you to the script. And all you'd have to do is modify that script slightly so that it pulled in Tickle files instead of SQLite files, and then you could, have Tickle 86.c or something like that. And not only would this make it go faster, but this would be really convenient for people like me who like to statically link against Tickle, because now I could just take Tickle 8.6, that file, and drop it into my project and compile it with my other C code, and I have a Tickle interpreter right there, ready to go. Now, there is something to be mindful of here in that this is a Tickle script that's generating the Tickle interpreter. So we've got a chicken or egg situation. You still need to be able to compile it as separate source files too, otherwise you'd never be able to bootstrap it. So your question was, are there compiler limitations? And Another technique that we use is after this file has been generated, we then have another Tcl script that runs, and it goes over and it breaks this file up into chunks that are less than 32,000 lines. It divides it at function boundaries. It breaks it up into chunks that are less than 32,000 lines, and then it generates one other file down here, which would be called Tcl86_all.c, which just sharp includes all these other little chunks. And that actually works with MSVC, and you get correct line numbers.
Because I ran into
But it's still a single translation unit.
similar problems when generating swig wrappers for my Tcl 3D stuff, which for open scene graph is very large, and then the Microsoft compiler said, okay, too large to optimize. If I can remember, I don't know.
It might have been an older version. I mean, I'm using like we don't use anything less than like 2010. Visual Studio 2010 and stuff, and we've not had any trouble. Now I know that some versions of Visual Studio you can't have long strings embedded in your code, so you have to. So we also have Tcl scripts that if we have big strings, it actually converts them into the initializer into the curly braces and the individual characters, which it will do. Whatever. So that's one really quick way to get some things done and to provide a lot of benefit. And that, I don't know, is anybody here like university faculty? I mean, this would be a great student project. You could make this an assignment for one semester, get this to work, and that would be really helpful to the community, I think. But that's not really what I wanted to talk about. I'm really talking about optimizing the C code at a low level. And the techniques that I've discovered here, this is kind of these are the tools that you need to do these techniques. One, you've got to have a high quality test suite because you're going to be making some very subtle low level changes, and it's very easy to introduce bugs. Now the test suite in Tcl is good. It's among the best, and amongst open source things. It could be better. But be mindful of that. You need a Tcl script that is going to be your reference, that's going to be your typical workload. And this makes a big difference. The chart I showed you with SQLite a little bit ago, it's a workload we've been using for a long time, and it uses the like operator of SQL. And so the like operator in SQLite happens to be very highly optimized because we're always trying to get that graph to go down. It does not use the substir function. So I'm guessing that a lot of optimization opportunities still exist in the substir function because we've never measured it. So this is important. Depending on what your problem is, that will affect how you end up optimizing. It needs to be deterministic so that you get the same answer every time. No threads, no randomness. It's always going to do exactly the same sequence of operations. To really do this well, you need a Linux workstation and a screen with a lot of pixels. You could in theory do this on a Mac. I think that Linux works better for this. I'll leave it to Mr. Landers to figure out how to do it on a Mac if he wants to. We don't know how to do this on Windows right now. But presumably, I mean, if you optimize it for Linux, it's going to run fast on all the other platforms too. And of course, a key tool that you need is cache grind. And so, and the thing that we're trying to, a quick detour. If you want better tests, I discovered this about a year ago. This American fuzzy Loupe is a fuzzer for looking for bugs in programs, and it instruments your code, and it monitors your code as it runs the test operation, and it looks at all the jumps it makes, and it sees when, and then of course starts changing the input to try and find new paths, and it sees when it discovers new behavior, and it's very, very good at finding behaviors in programs that the developers of the program never thought about. So this is a really great way to improve your test suite if you want to do that. But here's the algorithm for doing the microoptimizations. Did I explain what I mean by microoptimizations? I didn't. I missed that part, didn't I? I should have better notes. So Donald and Kevin are working on these great big changes that'll suddenly make things really go faster. With microoptimizations, what I mean is that we make changes where each individual change makes it run just a little tiny bit faster, so little faster that you can't even tell the difference. But if you make enough of these, they add up. And that doubling of performance in SQLite is the result of hundreds and hundreds, possibly thousands of individual micro-optimizations. Any particular optimization is unnoticeable, but the cumulative effect can be large. So this is the algorithm. You run your workload script using cache grind. Who's familiar with cache grind? Who has used cache grind before? A few people. What cache grind is, it's an Intel 8086 simulator type thing. It actually does, I guess, just-in-time compilation. But you run this thing, it runs a lot slower in cache grind. You run an ordinary binary in it. It runs a lot slower in cache grind, but it simulates the CPU and can actually count the number of cycles spent at each opcode. And I'll show you the output in just a second. So it does run a lot lot slower. What I find is that an application run under cache grind on a high-end workstation runs at about the same speed as that same application would run on an older cell phone. So that's a big difference. So anyway, so you run your workload using cache grind, and that gives you a big output which shows you the number of CPU cycles spent at each line of code. And then you study the output of that and look for places where you can make a few simple changes to reduce the number of CPU cycles used. And then you make the code changes and you test them to make sure they work. And then you remeasure to make sure that it really did make things go a little bit faster, and then you just loop this hundreds and hundreds of times. It is a labor-intensive process. It is not appropriate for general applications because it requires so much effort. But it is appropriate for libraries like SQLite, which is used a lot, and it's appropriate for the Tickle core because any change made in the Tickle core affects hundreds, thousands of applications. So here's an example of how to run it. All of the output goes into this file, cache grind.out, and then there's the process ID that uniquely identifies it. So you build Tickle Shell. You don't build it there's no special compile time options. It's just an ordinary binary. You do, I think, it wants to have the symbolic information, so be sure to include the -G. But then you run Valgrind is the name of it, and you say you want the tool cache grind, and then it's just the normal command. So it's just you prefix your normal command with the Valgrind tool, and it runs slowly, and it puts a lot of information into this cache grind.out.processid file. And then there's another little Tickle script that you need to run against that output file to clean it up, and it goes into some file that whatever name you want right there. And typically what I will do is before I start an optimization session, I will run this and get my baseline and call that cout baseline.tickle. That should say .text, excuse me. That's a typo. And then I'll make some changes, and then I'll rerun this again, and then I'll do a diff between the baseline and my current to see what actually changed. And that's very helpful to see how my optimizations are affecting things. This little script here is necessary in order to remove some artifacts and clean things up. Otherwise, the diffs won't work. There's the script right there. You can copy paste it when you go to do this. And you know how to get to these slides. I won't go into the details. So here's an example of an optimization, and this one is in SQLite. This is the before, and this is an output. This is just a small section of the output because the output is 200,000 lines long. This is a small section of the output, and it's showing various lines of code. And over here are the number of CPU cycles spent on that particular line of code. And Then I made a small change and it made it run faster. And I've highlighted the change right here. So the page number, this is in the logic of SQLite that is accessing individual pages of the database. And pages are numbered starting with 1. So page number is never less than 1. It's always 1 or more. And so originally it said if it's not equal to 1 and some other stuff, then, this is, we got the test for not equal to 1 here is initializing this Boolean. But then right after that, we have to check to see if the page number is 0, and if it is 0, then that's a corrupt database file, so we're going to throw an error. And I changed this not equal 1 to page number greater than 1. Because we know that the page number is never less than 0, this is really going to give us the same result. But the compilers, you see, are clever. And the compiler sees right here, if you said greater than 1, and that fails, and it immediately jumps down here, and it's going to test if it's less than or equal to 1. And the compiler optimizer will say, hey, I just did that test. I don't need to do it again. And so it gets to skip that test. But it couldn't skip this test up here. Not equal to 1 and equal to 0 are different things. It has to test it twice. So I've reduced the complexity by a single branch operation. And if you look at the timings here, you can see that, in fact, fewer CPU cycles were used. In this particular case, it saved about 500,000 CPU cycles out of 675 million, for a savings of about, almost 0.1%. Okay, reality is, there was no way in the world that you can measure 0.1% performance increase using traditional techniques. You've got to have something like cache grind that is 100% repeatable, where you can measure the performance to 7 significant digits. If you're trying to measure it just using time or something like that, you're going to get way more jitter in your measurements. You'll never be able to make accurate measurements. So this is an example of a microoptimization. Won't show up in a regular application, but if you do enough of them, it adds up. So I thought, well, let's try this on Tickle. And so I just came up with a demo workload, and this is not a realistic workload, but I wanted a demo. So I did this particular demo workload, and I ran it with Tickle, the trunk from a while ago. And part of the output gives you kind of a summary of how many CPU cycles are being used by each procedure in Tickle. And I was just scanning this looking for high runners, and I said, what's this compare var key? Let's go look at that. And if we go look at that, this is compare var keys right here. And we see it's really just looking, it's got 2 keys and it's comparing them. And if you look at the timings over here, you can see it's doing some work here in the middle, but most of the CPU time is spent here at the beginning and here at the end. Not doing any real work. What is that about? How can, what can we do here? To understand what's happening, you need to know a little bit about how modern machines work and what the function calling conventions are. So in a modern CPU, which here it means 64-bit Intel or an ARM chip, because those are these days the only 2 processors that matter, right? You've got a bunch of registers, and the calling conventions are, you've got a bunch of registers. The calling conventions are that function parameters, the first few function parameters, are stored in some particular registers. And typically, the caller will also assume that the function that's being called will overwrite some additional registers. But the caller requires of the function being called that a big chunk of registers over here be preserved. It expects those to be the same when the function returns as when they were when the function was called. So the subroutine cannot use any of these registers here, or if it wants to use one of those registers, it has to first save them on the stack. And so that's what all those cycles at the beginning and end were about. it was saving, let me go back up. Right here, it's pushing a bunch of register contents onto the stack, and down here, it's popping them back off the stack. And as you can see here, it's spending way more time pushing stuff on the stack and popping it off the stack in order to get in and out of the function than it's actually doing with the function. So what can we do about that? So the rule is registers have to be pushed onto the stack if the subroutine uses a lot of registers and just needs the space, or if there's a subroutine call. Because if there's a subroutine, if the function has a subroutine within it. So, and that's the case in this particular function. Up here it's all inline code, but then we call tickle get string and tickle get string. Something to watch though. You can see right here that most of the time we're running and we never get to the point where we call these subroutines. It never happens. You can see that from the numbers here, much smaller than the numbers right here. So most of the time we don't really need to be saving those registers. So how can we convince the compiler not to save those registers in the majority case where they don't need to be saved? So the way you do that, oh, that's the next slide, is to break this function into two pieces. This is the original function up here, and it starts running, and for the common case where it doesn't have to call subroutines, it just returns. For the uncommon case where it does need to save registers, it returns, but it uses tail recursion. It's the very last thing. And if it's tail recursion, it doesn't have to save things onto the stack. This is actually the way the compiler generates this. It's not it doesn't use the call instruction for a subroutine call. It just jumps directly into the subroutine, and then when the subroutine returns, that returns from the main program. So, and so we can see that now with this change, there is no pushing or popping. That's actually the return. There's no pushing or popping of values off of the stack for the main routine. Now you still have to do it if you call this subfunction down here. There's still pushing and popping, but that subfunction is called much less frequently, and so there's a lot less going on. Now there's an important detail here, and that is that we had to insert this macro tickle no inline. If you leave this out, and this is a static function, the compiler will recognize, oh, this function is only called from one place right here. I'll just inline it. That'll be helpful, right? Well, not really, because then it causes a bunch of static. So you've got to put that in here. And that macro is defined here. And this, so we've got a version for GCC, and that also works for Clang. And we've got another version for MSVC, and for other compilers, this optimization just doesn't work because we don't. I mean, are there any other compilers that we need to be worried about? And if so, we can extend this at some point. Now, this is in the tree. This code is in the tree, but it is on Miguel Sofer's private branch. It has not made it onto trunk. So we should think about maybe merging that at some point. So with, let's go back. Where did I? Where is my, where did I say how much better this is? Oh, there it is. So by splitting that function into two this way, we're saving 4 million cycles out of 262 million for about 1.5% faster. We're at this point, 1.5% faster, you say, oh, that's nothing. Yeah, but you know, that's almost to the point where you can measure the difference using a real-time clock. And you know, you string 100 of these together, and hey, you're really making progress. When I'm optimizing SQLite, if I can get a 1.5% faster in a day's work, that's been a good day. So this really is a kind of a labor-intensive thing, but it pays big dividends. This change is, the change I just showed you was not checked in because Miguel found a better way to fix the frequent calls to compare var keys. And I think that's on trunk. We need to check. We need to check. We need to check. So he checked that in separately. So here's another example, and I found this one. Carl and Kevin and I were working on this at the last Tickle conference, and we found this one. This is a different workload. It's some workload that Carl came up with us, and as you can see, one of the really hot runners here was pthread get thread specific data. So we brought that up in cache grind, and this is what the code looked like. This is the what was happening. So we didn't really have to mess with pushing and popping of registers, so that wasn't a problem. What it was doing, it was checking to see if the pthreads had been initialized, and if not, it was doing the two-stage, first check and then do the mutex thing, and then it had to create the thread-specific data and not. But this ran very, very seldom. And then it did tail recursion against pthread get specific. But this if instruction here was taking 17 million cycles. And Kevin Kenney got to looking and eventually determined that this routine is never called, but that, or how was it that he did it? It's only called from one place. When it matters. And so for that one place, we were able to get rid of this instruction altogether, get rid of the whole initialization thing altogether. So it really is just calling thread-specific data. Here's an example where it showed up where you're doing a test over and over, and it's just a test of a simple Boolean. You'd think that doesn't take any time. And it doesn't unless you're doing it 17 million times, and then it takes a fraction of time. So we checked in that change where we just removed that stuff. And so this routine suddenly runs a lot faster, and we saved 17.3 million out of 2 billion cycles, or 1% faster. And that was about 15 minutes of work. These things add up. So key points I wanted to make. I don't know if you've noticed, for the longest time we really didn't worry about CPU performance, because rather than trying to make your code run 2% faster, you wait 2 weeks and you buy a faster CPU, because they were going faster all the time. But we haven't had a faster CPU come out in 4 or 5 years. Now they're putting more cores on. What I see happening now is that you're getting a lot more memory and a lot more disk space, but the CPUs are actually getting a little bit slower. I don't know if you've been following the specs. And so if we want to get faster performance, we're going to have to start optimizing the code more. We believe that Tickle is ripe for this. I really think that we could double the performance of the interpreter by doing these micro-optimizations. But it is a lot of work. You've got to have cache grind or something equivalent to get repeatable measurements. There's no way that you can make these small changes and measure them using timing techniques. It's got to be simulated using cache grind. A lot of small improvements add up over time, and we can, in fact, do this. That is the gist of my presentation. I will open the floor to questions. I saw Christian's hand.
You do this measurement using Intel CPUs, right?
I do, because yeah.
Can you translate it directly to ARM CPUs?
I don't. Do we have a Valgrind that runs on ARM? I don't know.
Let's say some other CPU.
Yeah, you know what? So our measurements are being done on Intel CPUs, and I'm assuming that improvements for Intel will translate to other architectures, especially if they're similar in the sense that they have a large number of registers.
Okay. What about the influence of the size of caches?
Yeah, how do you measure that? I don't know.
But can you grind to take maybe 1 megabyte or only half a megabyte cache into account?
You can configure that.
Yeah.
I just use the default. Once again, and you know, and a lot of people object to this in that cache grind is not giving you necessarily a really accurate count, but it is giving you a repeatable count. And the point is not to be super accurate, but to be super repeatable, so that I know that my change makes a difference. And you know, a different chip, a different version of an Intel chip might give different CPU cycle counts because of differences in cache size or whatever. But the changes that I'm making in these micro-optimizations will help regardless. They might help in slightly different amounts, but they're still going to help. Likewise, these changes only reflect the code that is generated by GCC. We assume that this will also help with the code generated by MSVC. We don't really have any way of measuring it. I have double checked in the sense that you know, after you do hundreds of these and you get to the point where you can do timing measurements, it does in fact show up that MSVC runs faster. But I can't measure it on MSV on a single change. You have to have a bunch of changes where you can get to the point where you can measure it with timing. Yeah. Yes, sir.
Your very first example showed actually two differences. Is that second difference also?
All right, let's go back and look. What did I miss?
Just change the second difference.
Yeah.
I think that was to make it.
That's right. That's
That
the
was
one.
why the test.
Oh, yeah. I guess I did have to change this one. I didn't highlight that, did I? Okay. Yeah, so down here, I'm really testing what I really want to know is the page number 0. But I added this additional test here of is the page number less than or equal to 1, because then I knew that it would just skip the whole shebang because of the previous test up here. Yeah, you really have to think like a compiler. We were having a discussion at dinner the other day about should new computer programming students learn to program in assembly language? And there are differing opinions on this, both in this room and in the wider world. But you've got to, I don't know 8086 assembly language, but I know the principles of assembly language, and so I'm able to figure out what's happening here. If you don't understand, if you're a new student coming out of college and you have never had exposure to assembly language, there's no way in the world that you'd figure this out. So here's an argument in favor of students having some exposure to assembly language. Yeah, thanks. Hey, thanks for spotting that. I completely missed that. Yeah.
If you look at the difference from cache grind, if you compile just straight -G versus -G with optimization turned on.
Well, it doesn't. I haven't really studied that. I mean, no, because I'm trying to optimize it as delivered, and I'm going to deliver it with optimizations turned on.
But you're not testing it that way, are you?
No, I'm testing it with optimizations turned on.
Optimization.
Full optimization. Yeah, because without.
You didn't mention that in the slide.
Okay, yeah. So I'm testing with full optimizations because unless you turn on full optimization, or well, I say full optimization. I typically use -OS, because if you do 06, there's so much code movement going on that it's really difficult to correlate CPU cycles to lines of code. But OS keeps things pretty well localized. Oh, the OS means optimize for size. Do all optimizations that don't make the executable get bigger. And if you don't have the optimizations turned on, the compiler will not pick up on this optimization here. And it will always do both tests. And so this will be of no benefit to you. Yeah. Yes, sir.
And you told about the question, and then I keep the
We can talk
discussion
during
for
the break.
coffee break.
Yeah, okay.
Okay, so the last question. You said that amalgamation also improves the compiler optimizations because it can do internal over-procedure
Yes.
optimization. And of course, the compiler writers also figured that out, and they built link time optimization into the compiler.
You know,
Have you compared?
I have not, but all of the engineers at Apple keep telling me, no, you need to start shipping SQLite as separate source files because our fabulous Clang-based compiler will just do inter-procedure optimization. But they've yet to demonstrate that it's as fast, okay? And maybe someday that will help. And really to think about it, the other optimization that I did over here, where I broke that function into two, if you think about it, a compiler optimizer should be able to figure this out for itself at some point. They're just not there yet. Maybe in 5 or 10 years we won't have to do stuff like this. The compiler optimizers will get it on their own. But right now, I think this is the way to go. Yeah, or you can wait in 5 years and maybe you'll just recompile and be faster then. I don't know. Okay, out of time. Thank you very much.
Okay, thanks, Richard.